This conference will now be recorded.
Hello everyone. So today also we will continue quantitative analysis of organic compounds. So last day we have seen how to quantitatively analyze nitrogen and carbon and hydrogen, which is basically Liebig's method. So in this Liebig's method, now we will finish it by discussing a modified method for this Liebig's method. And once we finish this, next we will see quantitative analysis for other elements such as nitrogen, halogen, etc. and also related problems. So Liebig's method, it is suitable in case of organic compounds where carbon, hydrogen, oxygens are present. But suppose it may not be always so. If there may be some other elements also like nitrogen, sulfur and halogen. But when these compounds are these elements are present, then the method we have to modify slightly. So that we are going to discuss, that when nitrogen, sulfur, halogen is present, how we will modify the Liebig's method. So when nitrogen is present, as we have done the reaction with CuO, there will be also production of nitrogen oxides. It may be NO or NO2, but that is not wanted. After combustion, these will also be formed. So to remove these oxides of nitrogen, a spiral of copper metal is introduced at the combustion tube. And the purpose of using this copper metal, it will reduce the oxides of nitrogen to nitrogen gas. So from oxide form, now we are getting the elemental form, which is diatomic nitrogen gas, and it will escape unabsorbed. Fine. So in this way, we can remove the problem if nitrogen is present as element in the organic compound. Next, we will see if halogens are present. So when halogens are present, as we are doing the combustion with CuO, there is a chance that in presence of copper oxide, there will be formation of cupric halides. That means CuX2, cupric halides. Oxidation state is 2+, so that is why this will be the formula. It may be copper bromide, it may be copper iodide, but these cupric halides themselves can decompose to form free halogens. Now these halogens and volatile cupric halides itself, there is a chance that it will also get dissolved in KOH solution, because we also use potassium hydroxide solution in Liebig's method. But we want only carbon dioxide gas to be absorbed in KOH solution, because that is all about Liebig's method, where we quantitatively analyze carbon and hydrogen. But if cupric halides are also absorbed, then there will be error in calculation that we do not want. So to prevent this, now we are using spiral of silver metal. Just in the previous case, we have used copper, a spiral of copper. Now we are using spiral of silver. So it will be introduced in the combustion tube where combustion is occurring, and the purpose is that now we will convert the halogen into non-volatile silver halide such as AgX. So this is non-volatile, so it will not cause any problem. Now the third element, if it is present, which is sulfur. Now what we will do, if sulfur is present in the CuO that we use in combustion tube, we will replace it with PbCrO4, which is lead chromate. Now when lead chromate we are using, the sulfur dioxide that is formed during combustion from sulfur, so it will be formed during combustion. Now in presence of this PbCrO4 lead chromate, it will be converted to lead sulfate, and as a result it will be prevented from passing into the absorption unit. So in this way we can prevent this problem. Also this PbCrO4, it also helps if phosphorus is present. So PbCrO4 is also useful if there is phosphorus present in the organic compound, though that is not very common, but still if somehow it is present, then also PbCrO4 can help us, because now the oxides of phosphorus that will be produced during the combustion process, these oxides of phosphorus, now it will react with PbCrO4 and it will form non-volatile less phosphate. So in the previous case, that is in case of sulfur, we have seen the formation of non-volatile PbCrO4, which is which will not be absorbed in the KOH. Similarly, now there is non-volatile lead phosphate produced, that is Pb3PO4 whole 2. So this type of non-volatile lead phosphate will be produced, so it will not cause ultimately any problem. So that is all about the modified method, Liebig's method. Next, we are going to start quantitative analysis or under the heading of quantitative analysis of organic compounds. Now it is estimation of nitrogen. Now for estimation of nitrogen, this is the first method, because there will be another method also. This is the first method, which is known as Dumas method. Now what is the principle based on which we are doing this method? It is based on the fact that nitrogenous compounds, when we are heating it with cupric oxide, that is CuO, in an atmosphere of carbon dioxide, then it yields free nitrogen. And in this case, the apparatus that we are going to use, there is mainly three sections. One is CO2 generator, then there is combustion tube, and then there is ship's nitrometer, where nitrogen gas is collected and its volume we can measure. So this is the complete setup, as you can see. Now the total system, there is basically CO2 atmosphere will be present. We don't want any air atmosphere, or because if there is air, there will be oxygen that we do not want. So the whole atmosphere inside this setup, that will be CO2. So that is why there must be some CO2 generator. Now CO2 can be generated by treating lime with HCl, that is calcium oxide will react with HCl, and there may be formation of carbon dioxide, and then from sodium bicarbonate also we can produce CO2. So in this way CO2 generator must be there, which will create CO2 atmosphere. Then we have the actual combustion tube, which is this part, and here you can see total 4 sections are there. First there is CuO gauge, which is cupric oxide gauge. It is mainly used to prevent the back diffusion of the gases that will be produced after combustion, to prevent back diffusion. Then in the second part B, there is organic compound mixed with CuO, and that is the actual combustion mixture that we are going to use. Then in the third section we have coarse CuO. Now this will also help to oxidize the organic vapor that will be produced from organic compound. And the fourth section D, there is reduced copper gauge. Now this copper gauge will help to reduce the oxides of nitrogen if it is produced, because this NO and NO2, if it is produced, this copper will reduce it to free nitrogen. So these are the function of these different compartments. Now ultimately nitrogen will be deposited or stored here in this part, and here the blue part that you are seeing, that is basically KOH, because when you are doing this combustion, the organic compound which will be heated with CuO. Now not just oxides of nitrogen, there will also be formation of CO2, and the atmosphere is also CO2. But CO2 we will not measure. Our focus is to measure nitrogen only, that is the nitrogen element that is present in the compound, which will be ultimately converted to diatomic gas. But in this part there will be only nitrogen, and this KOH that will help us to absorb the excess CO2 that is present. So first, when we will start the process, that is before combustion, the atmosphere will be CO2, that is inside that apparatus there will be only CO2 atmosphere, and once it is done, then also CO2 gas will be, that is, it will be inserted through this whole apparatus, so that there is all the nitrogens are expelled, because if some nitrogens are stored inside this, that we do not want. We want all the nitrogen gas that is produced in the whole compartment because of this combustion. All the nitrogen should be in this part, so that we can measure it. So that is why CO2 gas will be inserted, so that it can expel all the nitrogen to this part. So in this way we will have to, that is, the process is done. Now once it is done, the next thing that we have to find is, we will find the volume of nitrogen. So in this part, suppose the volume of nitrogen is V1 liter. You can also do the calculation in terms of ml. It doesn't matter anything. Suppose we are considering it as if it is V1 liter. So this value you can get from the this part of this apparatus. Now the actual calculation, but before going to the calculation, here you can see this equation, which is very important because sometimes based on this equation you can get some problem. So this equation will help you to solve some problems, and it looks very at a first glance it maybe seems difficult, but actually not. See, here we have this organic compound OC, organic compound, where X, Y, Z, these are the number of atoms of carbon, hydrogen, nitrogen. Now, when we are using 1 mole of this organic compound, the number of moles of cupric oxide is 2x plus y by 2. And X and Y values you can easily get from the formula of organic compound, right? So if you know the formula of organic compound, you will be able to calculate what is the number of moles of CuO that is required. And for 1 mole of CXHYNZ, the number of moles of CuO is 2x plus y by 2. And in the right hand side, there is X moles of CO2 produced because only X moles, X carbon atoms are there. So obviously X moles of CO2 will be produced. Then we have Y number of H, that means Y by 2 H2 will be produced. NZ, so Z by 2 N2 will be produced. So these coefficients, all these values you can easily get if you know the molecular formula of the organic compound, and also how many moles of Cu will be produced, which is same as this number of moles. So this is the significance of this equation. Now the actual calculation. As we know, volume of nitrogen we have already calculated, which is V1 liter. And suppose the room temperature is T1 Kelvin. If room, it is at that is T1 Kelvin, and suppose the atmospheric pressure is P millimeter Hg. And if it is so, then pressure of dry nitrogen, that will be equal to P minus P aqueous. Now P aqueous is the pressure because of the aqueous tension. So that you have to subtract from the atmospheric pressure. So ultimately the pressure of nitrogen you are getting, which is P1. So you now know what is T1, you know P1, and you also know what is V1, which is already recorded after the experiment. Now there will be 3 more, that is P0, V0 and T0. Now these 3 are basically at STP, the corresponding pressure, volume, temperature at STP for dry nitrogen. Remember, it must be dry nitrogen. There should not be any moisture present, otherwise there will be error in calculation. Now we will use the equation, that is P0, V0, T0 is equal to P1 V1 divided by T1. Now here we need the value of V0, that we need. What is the volume at STP? Because if you know the volume of any gas at STP, then you can easily calculate the number of moles. Because we know for any gas at STP, 22.4 liter of any gas is actually 1 mole of that gas. So that is why we are calculating V0, which is the volume of dry nitrogen at STP from this equation. So V1, P1, T1 divided by T0 and P0. So once you solve it, now this T0 is nothing but 273 Kelvin and this one is 760. So this you can easily put, and V1, P1, T1, that you will get, T1 is the room temperature where you are doing the, at which you are doing the experiment, and P1 you can calculate from P minus P aqueous, and V1 will, volume can also be recorded. So here you will find the volume V0. Next, the calculation we will do. We know that at STP, 22.4 liter. All the calculation will be in liter because we have considered V1 in liter. So this liter of nitrogen, that is actually 20 gram of nitrogen. So V0 liter of nitrogen, that should be 28 divided by 22.4 multiplied by V0 gram of nitrogen. Okay. So now you know what is the mass of nitrogen, which corresponds to V0 liter. Next, the final calculation, that is percentage of nitrogen in m gram. Suppose m gram is the organic compound. M gram of organic compound. So here it is basically mass of N divided by mass of organic compound, which is M, multiplied by 100. But what is mass of M? That you have just calculated. Mass of M is basically this part. So 28, just write the same thing here. V naught divided by M multiplied by 100. You can also simplify it. Okay. So this is the percentage of nitrogen. In this way, you can calculate in the given compound m gram of organic compound. Now, based on this, we will solve one problem. Two problems basically we will total solve, and two problems you will see both are based on Dumas method, but the way it is asked, it is different. So to solve the first question, basically you need this equation that we have already seen. Now, why we need it? Because it is asking the number of moles of cupric oxide that will be utilized in the Dumas method for estimation of nitrogen in a sample of 57.5 gram of. Now see, an organic compound name is given. Name is given, not structure. So what you have to do? You will first draw the structure. From the structure, you can calculate what is the total number of carbon, hydrogen, nitrogen. Once you know this, you will get to know the values of X, Y, Z. And if you know X, Y, Z, you can easily calculate the number of moles of CuO that will be utilized. Okay. So first we will draw the molecule. N-dimethyl amino pentane. Pentane, that means total 5 carbon will be there. And at last point, there will be NMe2 because the positions of amino group is not mentioned. So you can put it in the terminal position. 1, 2, 3, 4, 5, total 5 carbon. Then NMe2. Dimethyl amino pentane. Dimethyl amino, not just simple amino. If it is written as amino pentane, then it will be simply NH2. But it is NN dimethyl. That means with nitrogen, the 2 hydrogen you have to replace with N. Now, if this is the molecule, total number of carbon is C7. 5 carbon and 2 carbon coming from 2 methyl group. Total number of H you can count, it will be 17, and number of nitrogen is N. So here we can write X, our X is 7 and Y is 17. Z we don't need. Now, if we know this, we can calculate what is the value of 2x plus y by 2. But before that, we will find out molar mass of. Now that will be equal to, if you calculate it, 84 from 7 carbon, 17 from 17 hydrogen, and for nitrogen it will be 14. So you will see, you will get 115 gram. So this is the molar mass. Now if it is molar mass, now we will calculate the value of 2x plus y by 2 because that is the number of moles of CuO. 2 into 7 plus 17 divided by 2. So 14 plus 17 by 2, it will give you 45 divided by 2 moles of CuO. So this number of moles of CuO required if your organic compound is 1 mole. But what is the number of moles of organic compound? That we have to know. So this is the given mass. So number of moles of the organic compound is given mass 57.5 divided by 115. So this is 0.5, that is half. So for 1 mole, the requirement is 45 divided by 2. So for 0.5, it will be multiplied by 0.5. So this is the number of moles of CuO that is required. Okay. And this is 11.25, but we have to express it in this format. So I will write it as 11.25 10 to the power minus 2. So this is the answer, nearest integer. Fine. Now the next problem, when we will solve this equation, we don't need. Now two ways you can solve this problem. First of all, remember this formula that we have already determined. You can directly use this formula. If you know V0 value, that is the volume of nitrogen at STP, and if you know the initial organic compound from which we have started the experiment, simply put it, you will get the answer. But I will suggest, even if you can't remember this formula, if you can remember, it's fine, directly put it. But even if you can't remember, it's okay. Because sometimes the question can be framed in such a way where direct value of V0 and direct value of M you cannot get. So in that case, you have to do it logically, not simply directly using this formula. So that is why both the ways we will solve the problem, and according to your convenience, you can do whatever way you prefer. So first method that we will use, simply use the formula that we have already determined. Because the problem is given in such a way, you can directly get this value. So 0.2 gram of organic compound, which is our M, are subject to estimation of nitrogen by 2 mass method, in which volume of nitrogen evolved at STP 22.400 ml. So these values are given. Percentage of nitrogen you can calculate. Now here, if we put it 28, 22.4, but remember when we have determined this formula, all the volumes are in liter. Now in this case, it is given in 22.4 ml. So you have to convert it to 22.4 multiplied by -3. So ml you have to convert to liter, then only you can get the correct result. Okay. Then divided by 0.2, which is the mass of organic compound. Now you can write it like this, which is this 2 by 10. That means now it will be 10 to the minus 3, 10 to the 3. So ultimately you will get 14. Now another way also we can solve this problem. Now what we'll do, we will first find out what is the moles of nitrogen. So moles of nitrogen, this is the given volume in ml at STP, and we know at STP, if 22,400 ml is the volume of 1 mole of any gas, and if you consider it in liter, it will be 22.4. So now we will divide it by 22400 ml, and we will get the number of moles. Now if this is the number of moles, then moles of n atom, number of moles of n atom will be double of this value, 2 into 10 to the power minus 3, right? Then mass of n, that is equal to 14 multiplied by this number of moles, because 14 is the atomic mass of nitrogen. Finally, percentage of nitrogen. That means mass of nitrogen, which is this value, divided by organic compounds mass, which is 0.2, 100. So again you will see, you will get 14%. So whatever way you follow, you will always get answer will be same. But first one is directly we are using the formula, but method 2 is stepwise logically we are following. Whatever informations are given, we are utilizing that, and we are getting the final result, 14. Now the second method of estimation of nitrogen, which is Kezel's method. This method is largely used for the estimation of nitrogen for organic compounds that are present in fertilizer, foodstuff, drugs. Now here, unlike Dumas method, where the reaction is simple, maybe calculation is little lengthy, but reaction is simple. You are just taking organic compound, you are heating it with cupric oxide, you are getting free nitrogen, and from the volume of free nitrogen, rest of the calculations are done. But in this case, the reactions, you will see total 3 to 4 steps will be there. So we will try to understand the process in stepwise manner. It is based on the fact that when an organic compound, which is obviously containing nitrogen, you will heat it with concentrated H2SO4. Now the nitrogen which is present in the organic compound, that will be quantitatively converted to ammonium sulfate. This will be the fate of nitrogen that is originally present in the organic compound. Now in this case, as I have said, stepwise we will try to understand all the reactions and also the experiment. So the first step of the experiment is we will do degradation. Now degradation means you will take the organic compound, known mass of organic compound you will take. Suppose you have taken m gram of organic compound, you will heat it with concentrated H2SO4 in presence of potassium sulfate and a little amount of CuSO4 or mercury in a long necked flux. From the picture you can understand it is a long necked flux which is known as Kegel flux. We have taken all this mixture K2SO4, copper sulfate or Hg, then concentrated H2SO4 and obviously the organic compound. You are heating it, so you are degrading the organic compound so that the nitrogen comes in the form of ammonium sulfate. Now why we are adding K2SO4? It raises the boiling point of H2SO4 and ensure complete reaction. And why we are using CuSO4 or Hg? Because it acts as catalyst. So this is the reaction. Nitrogen which is coming from the organic compound, and we are getting this nitrogen in the form of NH4-2SO4. Now one thing you have to be sure, suppose you have X moles of ammonium sulfate, so the corresponding number of moles of nitrogen will be double because the formula is NH4-2. So all this will be required in the final step, not now. Now the second step, once you have obtained ammonium sulfate, in the second step you will boil it with excess of sodium hydroxide. So this reaction will produce ammonia gas. So this will be liberated. Now this liberated ammonia we will absorb in known excess of standard acid. Standard acid means you have taken some volume of acid, maybe H2SO4 HCl. You also know its concentration. So that is it is standard acid. So ammonia which is basic, it will be easily absorbed in H2SO4 or HCl. So this is the setup. Contents of Kegel flux after digestion, that is after the first method, after degradation, you are treating it with NaOH, you are now heating it. There will be ammonia liberation, and this ammonia which is liberated, it will pass through this condenser. That means the vapor will be condensed, it will be converted to liquid ammonia, and it will be mixed with this standard acid which is taken in conical flux, known volume of standard acid. You also know the concentration as well as volume. So ammonia, it is now captured in this conical flux. So the related form reactions that are going on here, ammonium sulfate when you are treating it with NaOH, look at the ratio. Ratio is very important. Especially during the calculation, you will understand why it is important. So 1:2 is the reaction, you are getting 2 ammonia. So from 1 mole of ammonium sulfate, you are getting 2 moles of ammonia. And the second reaction, which is happening in the conical flux, suppose you have taken sulfuric acid. So it is 2:1 reaction. Again, we are getting ammonium sulfate. Now, if you are thinking ammonium sulfate was already there, then what is the point of converting it to ammonia and then again we are getting ammonium sulfate? So try to understand why we have done it. The reason why we have done it, if you directly have this ammonium sulfate, then the measurement, and if you have it in this form, because now you have taken excess of acid. So when there is excess of acid, after formation of ammonium sulfate, some extra acid will still be there because you already deliberately you have taken extra acid. Now this extra acid, if you measure, if you back titrate with some base, then you will get to know the number of moles of this extra H2SO4. If you know this number of moles of extra H2SO4, you will also know what is the number of moles of H2SO4 actually consumed with ammonia, because you know the starting moles of total number of moles of H2SO4. If you know the extra H2SO4 unreacted, obviously you will know what is the reacted amount of H2SO4. So if you know this, Then number of moles of ammonia you know. If you know number of moles of ammonia, you know the number of moles of ammonium sulfate. If you know the number of moles of ammonium sulfate, you also know the number of moles of nitrogen atom. So this is the purpose why we have done this extra step. That is, ammonia is produced, then ammonia is again reacting with H2SO4. Now this is the second step of this experiment, and in the third step, final step, back titration. The acid left unreacted, that is the extra acid. Now we are titrating it. It is called back titration because we have not taken it freshly. We have done some reaction, then there is some extra acid that we are treating it with a standard alkali solution. It may be Na2CO3 or it may be NaOH. Now it is also standard. You already know the concentration of NaOH. So if you know its molarity, if you know its volume, you can also know the number of moles of H2SO4 consumed. This is again 2:1. Okay. So these are the principles based on which total 3 important steps are there. First of all, degradation, then liberation of ammonia, capture of ammonia, and finally back titration. Now in the whole experiment, as a note, you have to remember this method is applicable in specific cases. There are some cases where you cannot apply this method because this method is all about converting the nitrogen of organic compound to ammonium sulfate. But when you have nitrogen atom in the form of nitro, in the form of azo group, N double bond N, and for compounds having nitrogen directly present in the ring, such as pyridine. So pyridine directly attached in the ring, or quinoline, where it is also directly attached in the ring. So in these cases, it is difficult to convert the nitrogen atom. Okay, one more point. Or two oxygen atoms. That is nitrogen if it is directly attached to oxygen atom. So in these cases, conversion of nitrogen to ammonium sulfate doesn't occur, and that is the reason you cannot use Casal's method when you have nitrogen in this form. So you can also get question regarding this. There is already question in exam. So be very careful. Now we'll do the calculation, and for doing this calculation, we need all these reactions that we must know. This is the first method where we have degraded the compound. The second reaction, third. So these two together, degradation, liberation and capture. And this is the fourth, back titration. Now here, suppose we'll start from the volume of excess H2SO4 that you have used in third step. And here all the molarity is M molarity. So I will not write it again and again. I have already mentioning it here. Molarity, suppose is M molarity. I am doing it in general. I have not taken one molarity. M may be 1, it may be 2, it may be 0.5. So it is M molarity. So this is the volume V ml. Now the volume of NaOH, that is also M molar. I am not mentioning it separately. Just consider all the molarity as M molar. Volume of excess H2SO4 that will be required for titration. That is for the fourth step. Obviously, whatever is your volume for H2SO4, this volume, it will be different, right? So for volume of, because molarity is same. So directly from the coefficient, you can understand what will be the volume ratio. So volume of NaOH, this Vm. Volume of NaOH required for titration, suppose it is V1 ml. Now, if it is the case, then the equivalent amount of H2SO4 will be, this is equivalent to V1 divided by 2 ml of M molar H2SO4. Because if the volume required for NaOH is V1, H2SO4 volume will be half of it because the ratio is 2:1. So it will be V1 divided by 2. Next, volume of H2SO4 react, which is consumed with ammonia, or I can write reacted with ammonia, consumed during this reaction, that will be total volume divided by V1 by 2. sorry, V1 by 2, because you have started from VML. This is the amount. Now, if this is the volume of H2SO4, then volume of ammonia, that must be double. That is equivalent to, it must be 2 into V minus V1 divided by 2. This is the volume of ammonia. Now we will go to the final calculation. That is, suppose you have 1000 ml 1 molar ammonia. Then what will be the corresponding mass? It must be 17 gram of ammonia, molar, which is the molar mass. 1000 ml 1 molar ammonia is nothing but 17 gram of ammonia. Similarly, if it is m molar rather than 1 molar, then it must be 17 multiplied by m gram. And if it is 1000 ml m molar ammonia, not ammonia, suppose if it is nitrogen. Now 1 mole ammonia is basically equivalent to 1 mole nitrogen. Now instead of multiplying 17, I will multiply 14. So this is the mass of nitrogen, not N2. It is N. That is why it is 14, not 18. So if it is the case, now we can say this is for 1000 ml, but we need it for this ml. So for 2 into V minus V1 divided by 2 ml m molar, in this amount, the mass of nitrogen will be 14 m divided by 1000 multiplied by 2 into V minus V1 divided by 2. Okay. So finally, we know what is the mass of N atomic nitrogen present in this volume of ammonia. So now the final step, percentage of ammonia is mass of nitrogen, which is this total amount, divided by mass of organic compound from which we have started. So this will be the final formula that we are reaching. 14 into molarity So this is the formula you can directly use if you already in the question, if molarity is mentioned, V is mentioned, V1 is mentioned. But again, I will say if these values sometimes you may not get directly in the problem. So in that case, you have to solve the problem logically, step by step. So next we have this, we have to solve this problem. So we will use, if I am using directly the method formula, then that will be method 1. So when it is method 1, first read the question. 1.4 gram of organic compound. So you know what is the value of M. Digested by Kejal method, and the evolved ammonia was absorbed in 60 ml M by 10 sulfuric acid. So M by 10 is the molarity of sulfuric acid from where you have started. This is the initial amount. Then unreacted acid required. This volume, 20 volume ml of M by 10. So molarities are same. So directly you can put the volume in the formula that we have just determined. So here 20 ml, that will be basically V1, and 60 ml, that will be basically V. And M you already know, which is 1.4. So using the formula that we have just calculated, if you use it and if you put it 14, molarity is 10, 1 by 10, 60 minus 20 divided by 2, sorry, it is 1000, not M, I will write 1.4. So if you do this calculation, you will ultimately find the answer as 10. Okay. Now this is, we are 10%, so that will be the answer, that is option D. But you can also logically solve this problem, which basically I prefer more because it is a general way to solve. And for this, you don't have to remember all these formulas. So 20 ml m by 10 NaOH. So volume is in ml and molarity is 1 by 10. That means millimoles of NaOH that you can get by directly multiplying 20 with 1 by 10. So this is 2. Now if it is the case, then 1 millimole H2SO4 is the amount of H2SO4 reacted with this NaOH. Now if it is the case that is reacted with NaOH, but you have started H2SO4, what is the number of millimoles? That is initial, which is nothing but total amount of H2SO4, 60 ml multiplied by m by 10. That means it is 6 millimole. So 1 millimole H2SO4 reacted with 2 NaOH, that is the ratio. 6 millimole you have started with. That means millimoles of H2SO4 reacted with ammonia, that must be 6 minus 5, 1 millimole. Sorry, 6 minus 1, 5 millimole. Right? Now, if it is 5 millimole of ammonia, in terms of, sorry, it is 5 millimoles of H2SO4. Millimoles of H2SO4 reacted with ammonia is 5 millimole. That means millimoles of, let me erase it. So millimoles of ammonia should be double of it. That means 2 into 5 millimole. Now, if it is the volume of ammonia, that is amount of ammonia, then amount of nitrogen is also 10 millimole because one NH3 containing one N. So now finally I can write 10 millimole nitrogen, which is same as 10 millimole ammonia. We will convert it to moles. So simply multiply it with 10 to the power minus 3. So it will be 0.01 moles of N. So as we have reached already the final step, 0.01 is the number of moles of N. So if it is so, then percentage of nitrogen is mass of N divided by mass of organic compound multiplied by 100. So mass of nitrogen is number of moles of it multiplied by 14 divided by 1.4 multiplied by 100. So you can write it as 1 by 100, then 14 divided by 1.4, 100. So you will again get 10. So as it may seem apparently that it is lengthy, it is requiring more time, but it is very logical stepwise. So I prefer this one because directly if you are getting all the values, you can put it in the equation, but you may not get always. So whatever, it is up to you which way you want to solve the problem. Last one is the correct answer. Estimation of halogen. So in estimation of halogen, which is Carias method. So in this method, we are using a tube like this, hard glass test tube we have taken, and we have taken a known mass of organic substance. And suppose that is M. We are treating it with fuming HNO3 and also silver nitrate. So everything is taken in a sealed hard glass tube about 2 cm wide and 50 cm long. And this is called Carias tube, and that will be in the furnace. We will be heating it. And this total system, it is present in the iron jacket, this part. Now here, this based on this tube, which is Carias tube, the method is known as Carias method. Here carbon hydrogen actually always you will get it in the organic compound. but sulfur may be also present. That will be converted to SO2. And halogen, so if these elements are present, it will be their fate. C is CO2, H is H2O, S is SO2. But what about the halogen? As silver nitrate you have taken, so halogen will combine with AgNO3 and it will form a precipitate of silver halide. It may be AgX, that is, it may be AgBr, AgCl. So in this way, the halogen which we are trying to estimate, that we have already converted in the form of silver halide. Once the reaction is done, the tube is allowed to cool and a small hole is made in the tube to allow the gases produce escape. So all these gases, H2, it will be in the vapor form. So if you made a hole here, all these gases, that will be removed. You will be left with AgX because we are interested only in AgX, that is already in the solid form, PPT form, precipitate, right? So tube is broken, all the gases are removed. PPT you will filter, then wash, dried, and exact dried is very important so that no moisture is there. And finally you will take the mass. So this is the way we do this experiment. Now once it is done, next we have to do the calculation. So mass of AgX produced, suppose X may vary, it may be BrCli, not for F, only for 3 halogens. Now if it is so, number of moles of AgX, that is also equal to number of moles of X present in M1 gram, right? Now if it is so, then M1, if you divide it by the molar mass of AgX, you will get the number of moles of AgX, which is actually also equal to the number of moles of X, because per mole of AgX you have 1 mole of X. Okay, so that is why it will be like this. Now once it is done, finally percentage of, okay, now next step is mass of X in M1 gram of AgX. Now that will be equal to M1 divided by the molar mass of it, so I am not writing it again, multiplied by atomic mass of X. Now depending on whether it is CLV or I, it will differ, so that is why I am writing it in general way. And finally, the percentage of X. Now that will be this M1 divided by molar mass of AgX multiplied by atomic mass of X. Because now you are calculating doing the final step, that is the percentage of X present in m gram of organic compound. So this is the total mass of X. This whole quantity you have to divide with m and multiplied by 100. So this is the formula, final general formula, you can say. Now we will see for all the halogen, percentage of halogen is atomic mass of the halogen, which is this one. Now in the denominator you have 108 plus atomic mass of halogen. So what is 108? 108 is basically Ag, the mass of Ag, because total, you can also write it like molar mass of AgX, which is atomic mass of Ag plus, which is 108, atomic mass of Ag and atomic mass of halogen. So this will give you molar mass of AgX. So atomic mass of halogen in the numerator, you can see here. Then in the denominator, we have molar mass of AgX. Then weight of silver halide, which is nothing but M1. And weight of organic compound, we have written it in terms of M. Here it is written as W. But important point is, this is the final expression which you can directly use. Now, if it is chlorine percentage, see how it will vary. 108, that will be added to 35.5. This will give you the mass of AgCl, which is written in the denominator. and this is the atomic mass of Cl. Then weight of AgCl precipitate divided by the total amount of the organic compound. Similarly, when it is AgBr, 108 should be added to 80, which is atomic mass of bromine, and it will give you 188. This is atomic mass of bromine. And for iodine, 108 plus 127. So this will give you 225. So these are the three equations that you can directly use if you are solving any problem. Okay. Now we have this problem which is based on Carrier's method for estimation of bromine. It may be for any halogen, but in this case it is for bromine. When 0.15 gram of an organic compound was analyzed using Carrier's method for estimation of bromine, this is the amount of AgBr obtained. Percentage of bromine we have to find. Atomic mass is given for silver, and for bromine it is 0. Now remember the formula: M1 divided by molar mass of AgBr. See, in our case it is AgBr. Then multiplied by atomic mass of Br, 100 divided by M. So if we write all the values, M1 is 0, that is the given mass, 0.2397. Mass of AgBr is simply add these two. Atomic mass of Br is M is 0.15. So in the numerator we have 80.2397. In the denominator we have 188, 0.15. All this quantity multiplied by 100. If you do the calculation, you will get 68%. So this is the direct way to solve. But another way also we will solve this problem. So logically, if we solve, what we will do? We will find out moles of AgBr, which is also equal to moles of Br. And how you will calculate it? Given mass divided by molar mass of AgBr, 108 plus 80. So once you get this, the number of moles of Br, next what you will do, you will multiply it with 80 so that you can get mass of Br present in 0.15 gram of organic compound. Once you have obtained it, next you will divide it by M, which is 0.15 gram. That is initial organic compound you have taken. If you do this calculation, you will see again you will get 0.2397 divided by 180 multiplied by 80 divided by 0.15. So it is actually same logic, and again it will be 68%. So in this way we can solve the problem. Fine. Okay, here formula is also written. Whatever, we have already done it. It is 188. Weight of AgBr PPT, which is this one, and W is 0.15. We have another problem that is also Carrier's method. Consider the following reaction on estimation of bromine in 1 gram of R. R means the major product which you are getting when you are treating this compound, this aromatic compound, with red phosphorus and bromine. So here you have to know what is R. Then you can understand you can solve the total problem. So estimation of bromine in 1 gram of R. So this is present 1 gram using Carrier's method. The amount of AgBr you have to find. So this is the reaction. In presence of red phosphorus bromine, this OH will be converted to bromine. Now this molecule you have to find the molecular formula. Total number of carbon is 7, hydrogen 6, bromine 2. Now when you are doing this, treating this molecule with Carrier's method, and you get from 1 mole of this compound, you get 2 moles of AgBr, because per mole of this compound you have 2 bromine atom, right? Next, what we will do, we will find out the molar mass of this compound. That is molar mass of R. Given mass is 1 gram and molar mass is C7H6Br2. So 7 into 12, it is 84, plus 6 for hydrogen, and for bromine 80 into 2. So you will get the value 250. So 250, it is the molar mass of this compound. Okay. So if it is molar mass of R, the number of moles of HEBr, double. Two into 1 by 250. So this is the moles of HEBr. So to convert it to gram, simply you have to multiply with the molar mass of HEBr. So the molar mass of HEBr is simply at 108 and 80. So it will give you 188. So if you add it, you will get, this is the value. This is the, and this is basically will give us the answer. So this is the final answer in gram. And see, here some extra informations are there. That is phosphorus atomic mass. Basically, we don't need, though we are using red phosphorus, but you have to know what is the product form. Red phosphorus is simply converting OH to Br. So here, not just KES method, we also have to know some extra information. What is the product are, that is the extra information. But finally, we are using KES method, and we are getting the answer. Fine. So we'll end the session here. Thank you for listening.